Log on, tune in, find out. Another good idea from Cambridge.
Catharines College, Oxford, who's going to talk to us about his proof of Snevily's conjecture.
Yeah, is this thing on? Can you hear me? Yeah.
Is it switched on?
It is.
I think it's okay.
There's a red light. It's okay, okay. So, first of all, it's nice to be in Cambridge today to speak about my proof of Snevily's conjecture. The talk is going to be organized as follows. I will give the proof, but before that I would first like to show some of the background of the problem briefly, some motivation behind the problem, and see how it might arise naturally in its context in additive combinatorics. Well, Snevily's conjecture is about adding elements from two sets in an additive group, and this is the general setting of additive combinatorics. In general, we have two sets, let's say A and B, and we would like to be able to add their elements, so we would like them to be subsets of some group. In that case, we can form the sum of their sets, which consists of all elements of the kind A plus B, where A is in the first set A and B is in the second set B. And this is a very general setting in additive combinatorics, and we can go many directions from here. Most generally, try to relate the size of the sum set A plus B in terms of the sizes of the sets A and B. Well, maybe one of the first results in this area is the Cauchy-Davenport theorem from about 200 years ago, which says that in the special case when G is the additive group of a finite field of characteristic P, of size P, then the sum of the two subsets is bounded below by the sum of the sizes of the two subsets, as long as they don't fill up the whole group first. This theorem has a easy proof. There are about three completely different ways to prove it. It can be generalized in many ways. For example, one could try to could ask the opposite question: if the sum A plus B is sort of has size linear in terms of the sizes of A and B, what kind of structure does the sum set, and what kind of structure do both sets have? There are some very positive results in this area. Well, one can also, a natural generalization would be also try to prove a thing for general groups. This theorem holds for when G is, in the special case, when G is the additive group of a field. What happens if G is a general group? And there are also some very positive results in this area too. But the one we're interested in, and the one which leads to our conjecture, is the following. The equality in Cauchy-Davenport theorem is achieved when, for example, both of them are arithmetic progressions. However, although equality is achieved, in general the bound is not very good, because we can form the sum of if say A and B have sizes k, then we can form the sum in k squared different ways. And the lower bound is about linear in k. So we haven't proven much. And although we cannot improve the right side in general, what happens if we try to improve the left side? Well, instead of the whole sum, let us just consider special subsets of the sum of the two sets. For example, this is called a restricted sum set, and we only take those sums A plus B when A and B satisfy certain conditions. For example, a typical and quite difficult example is what happens when A is not equal to B in Cauchy-Davenport theorem. And it turns out, although Cauchy-Davenport has a relatively easy proof, this turns out to be quite difficult. It was a conjecture of Erdős and Heilbronn, and it was open for 30 years. We still have the linear lower bound for the sizes for the size of the sum set in terms of the sizes of the subsets A and B, with slightly modified constants. But we haven't improved much, because we still only disregard at most k of the sums, and still we form the sums in about k squared minus k ways, in at least k squared minus k ways. And the bound hasn't changed much, but also the set hasn't changed much. So a natural question to ask is, how far can we push this? How small a subset can we take from the sum of the two sets? And ask question about that. For smallest possible subset will be taken when each element from A would be summed with exactly one element from B. That can only happen when both sets have the same size, so naturally let's take both of them to be size k. And then we have the following question, which is like a follow-up to the question we raised before. If A and B have sizes k, and G is a finite abelian group, can we always pair up the elements, one element in A correspond to exactly one element in B, such that the sums are different? Or if not, how can we estimate this sort of set, A plus row A? Well, the most optimistic bound that all of the elements are different fails. For example, it fails when G contains Z2. Well, a counterexample could be when A and B are both the same subgroup of G, which has even size when G is commutative. But it seems that the evenness is the only obstruction, so in about 10 years ago, in 1999, Snevily formulated the following conjecture. If we remove the evenness assumption and we just say G is abelian, it has odd size, and we have two subsets of k elements. Can we always pair up the elements? One element from A corresponds to exactly one element from B, so that all the pairwise sums are k different elements from the group. This can be formulated in many different ways. For example, one way is using the subset and the bijection. Another way is seeing it as taking the additive table of G, when G is a abelian group of odd order, and then taking any k times k subsquare of the additive table. The conjecture is that any subsquare of the table must contain a latent transversal, which is a set of k elements, such that no t elements are in the same row, no t elements are in the same column, and all the entries are different. This is a reformulation of the statement. This relates it to latent squares, although it's not strictly speaking a latent square, but latent squares are also interesting by themselves and have many mysterious properties. There are also some very open conjectures in these areas. But the formulation will be interesting is the following. We are already given an ordering of the elements of A and B, say A1 up to AK and B1 up to BK. And we want a permutation of the indices of the elements of the second set, such that permutation pi, such that all the elements A1 plus B pi 1, so on, are pairwise different. We will prefer this formulation because we will be working with determinants, and this kind of sums will come up in expansion of a determinant, which we will then show that it is non-zero, and therefore it will be implied that these numbers are indeed different for some permutation pi. The conjecture was formulated in 1999, and soon after, less than a year after, it was proven for cyclic groups of prime order by Noga Alon in 2000. This is when the paper was published. However, this proof is actually referred to in the paper by Snevily in which he makes the conjecture, so it was probably made a few years before. Similarly, the following year, the same method, using the polynomial combinatorial Bushtelazat, was modified to show it for all cyclic groups. And the proof I will talk about now is from about a year ago, which shows it for all possible groups. Unlike the previous, which used the combinatorial Bushtelazat, this uses the linear algebra. So, tool in the proof is linear algebra and just some basic facts about fields and group homomorphisms. And the plan of the proof is the following. We have our group G. In general, if you want to study G, we want to study its representation. So we will study the dual group, the group of homomorphisms into the multiplicative group of some field. And if the field is nice, if it has enough roots of unity, G is commutative and finite, then this will be isomorphic to G if the conditions are suitable. Then we have a general theorem, which in our case will imply that the set of homomorphisms from a group to the multiplicative group of a field is linearly independent as elements of the function space from the group to the field. Well, in our case, if we choose F suitable and G is suitable, if both G is isomorphic to the homomorphism group from G to F times, then HomGF has exactly as many elements as you would expect in a basis. And since they are linearly independent, it will follow that they indeed do make a basis. So we can conclude that we can represent any map from the group to the field as a linear combination of homomorphisms. And homomorphisms have the nice property that they're multiplicative, and therefore determinants behave nicely, because as we will see, we'll get that many of the rows are proportional because the homomorphisms are multiplicative. And also determinants behave nicely under addition because they are multilinear maps with respect to the rows and the columns. And we will finish the proof by using some algebraic manipulations on determinants, which will use both these facts. It will use the fact that homomorphisms are multiplicative to show some proportionality between the rows, and it will also use the multilinearity of the rows of the multilinearity of the determinant to cancel out many of the rows in the calculations. So the first part of the proof is a technical lemma. It's a general lemma. I will include the proof just for completeness because it's not very long. It's by Dedekind, and it says that if G is a group, it could be a monoid as well, and F is a field, then the homomorphisms from G to F times are linearly independent. The set of all homomorphisms is linearly independent. And the proof is by contradiction. If we just assume that we have some linear dependency, we can take a linear dependency with smallest number of terms, and then all the coefficients will be non-zero. So let's take such a linear dependency. Let's say high 1 up to high s are homomorphisms. And let's say a1 up to as are non-zero scalars, such that the linear combination a1 high 1 plus so on plus as high s is 0. Well, the idea is applying this linear dependency to x and to xg. If we apply it to xg, then using the multiplicative of each of the homomorphisms, we can expand it as sum of ai high I of x times high of g. If we apply it to x and then multiply by high 1 of g, we can expand it as sum of ai times high I of x times high 1 of g. Then if we subtract the two, we'll get a smaller linear dependency, which must therefore be trivial because of our assumption that the original linear dependency was non-trivial, was minimal. And because the first term vanishes, this must be trivial, but all the as are non-zero, which means that all the homomorphisms coincide at G. Because G was arbitrary, all the homomorphisms must have been same, which is a contradiction. There are many ways to state it. This is one way, and there are also many ways to prove this. Now let's just go back. First of all, we will be interested in applying this to when G is a commutative of size m. It is finite abelian of size m, and F is a finite field. If F is any finite field, then the multiplicative group of F is cyclic. Therefore, as long as this size of this multiplicative group is divisible by the size of m, thus the size of the group G, then the dual group, the group of homomorphisms from G to F times, will be isomorphic to G. And therefore, as we have concluded previously, since hom GF is isomorphic to G, its size is also m. They are linearly dependent in general, and in this case the space itself has dimension m, and therefore hom GF must also be a basis. So it in fact spans the space of all maps. We will apply this to our group G, and we will also have an additional assumption on F that it is of characteristic 2, so that all the calculations work. Now let's just go back, forget for a minute about these two lemmas, and just go back to prove something completely combinatorial. In this case, we just have a k times k array of any element. Let's call them Gij, and let's say they are element of some G. In this case, it does not have to be a group because we don't need the additive structure. The only assumption we have to make is that in the k times k array, no two entries in the same row are equal, and no two entries in the same column are equal. And then if F is a field which has more than k elements, which is the size of the array, then we claim that there exists a function which maps from G to F such that the determinant, when we apply this function sort of to the determinant, to each entry of the determinant, we get a non-singular matrix over the field. Equivalently, the determinant of that matrix is non-zero. And the proof of this is completely combinatorial, and it uses induction. The simplest case is the case k is 1. In this case, we just have a 1 times 1 array, and the field has more than one element, so we just assign phi to this element, so that this element goes to some non-zero element of the field, and the determinant is trivially non-zero. Suppose, say that k is bigger than 1. Let's just take our k times k array, and let's call our first array, our first element in the first row and the first column, let's call it G. Then G may appear elsewhere in the matrix, but it cannot appear twice in the same row or the same column. Now, the determinant doesn't change up to sign when we permute rows and columns, or let's just say that this G appears only on the diagonal. Now, let's for a moment apply phi of G, but only as a symbol. We will assign it values as we go along. For now, just phi is some abstract symbol. Then expand this determinant by the definition, and we'll get some polynomials. Let's isolate this variable phi of G and consider the determinant as a polynomial in phi of G. Then its coefficient will be some polynomial in the other variables, phi gij. And in fact, the leading coefficient of this polynomial, because of minor expansion or Laplace expansion, will be the determinant of some submatrix. In fact, it will be the determinant of that matrix when we eliminate those rows which contain G and those columns which contain G. Now, this submatrix does not contain G, and it's of size less than k times k. Therefore, by the induction assumption, we can assign phi values over these symbols, the symbols which appear in this case and in this submatrix, such that the determinant of the submatrix is non-zero. Therefore, we can also assign phi values over all of the symbols except for G, such that the determinant becomes a polynomial with non-zero leading coefficient, also of degree k. So this polynomial will be a polynomial of phi of G. It will be of degree k, which is less than the size of the field. It will also be non-zero because the leading coefficient is the determinant of the submatrix, which we have chosen to be non-zero. And therefore, the polynomial cannot vanish over the entire of the field. This is simply using the fact that a polynomial of degree n over a field cannot have more than n roots unless it is trivially zero. So the polynomial is not trivially zero and of degree less than the size of the field. Therefore, we can finally assign phi the final value to G, and the polynomial will not vanish. Here we haven't used the fact that the GIs were only symbols. There is only an array of symbols, and we haven't used any structure. The case we're interested in applying this to is the following. We will have our group from our conjecture, and A1 up to AK will be some, and B1 up to BK will be some subsets. F will be a field of with more than k elements, so that we can apply what we have proven. And then we can form the array in which the ijth entry is ai plus bj. Now, for this array, there are no two entries in the same row which are equal. This is because all the bi's are equal. And if ai plus bj is a1 plus bk, then bj is equal to bk. Similarly, no two entries in the same column are equal because the as are different. Now, therefore, if we apply our previous lemma to this, we will get some function from G to F, such that if we apply phi to each entry of the matrix, getting the matrix phi of ai plus bj, then this matrix will be non-singular. It will have non-zero determinant. Now, let's just remember what we had. We have G, an abelian group of odd size m. Now, we will impose one additional requirement on F, that it will have characteristic 2. It was not needed up to here, but it will be needed in order for the manipulations with the determinant to work, and this is also where the fact that G has to have odd size will come out. So F will be a finite field of characteristic 2. It will, let's say it has size q, and the multiplicative group, which has size q minus 1. Q minus 1 is divisible by m, and also trivially this implies that q is bigger than m. So we can apply both our lemmas. Well, our second lemma says that we can find the function phi such that phi of ai plus bj, that matrix is non-singular. The determinant of this matrix is non-zero. From our first lemma, we can conclude that the set of all homomorphisms from G to F times, this set spans the space of all maps. Now, the idea is to represent phi in terms of these homomorphisms. We can do it because phi is the linear combination of the homomorphisms, and substitute phi in this form into the determinant, use multilinearity of the determinant in each of its rows, and see what we get. We can see that at this point, when we expand the determinant, we'll get some products of entries of the form phi of ai plus b pi j, where pi is a permutation. So this is sort of like what we want, but it doesn't tell us anything at this point because these are all just non-zero products, and we can't conclude anything at this point. However, we will be able to conclude something as long when we include the fact that all of the phi's are multiplicative functions. So let's just expand this. We have our matrix phi of ai plus bj, and we just substitute phi. Instead of phi, we write a linear combination of the homomorphisms. So then each row can be represented as a linear combination of m rows. We obtain each of the rows by substituting phi by phi I, which is the ith homomorphism. So we get each row is a linear combination of m rows, and there are k rows. So we get m to the power of k terms in the expansion. Each term will look like the following. We will take our determinant, which is phi of ai plus bj, and then in each row, instead of phi, we substitute phi with some homomorphism. There are m times k possibilities to do this. There are m possibilities for substituting the homomorphism in the first row, and for the second row, and so on. And in addition, we will have the coefficient in front of these determinants. These are just the lambdas, which occur from the fact that we can phi is a linear combination, not just a sum. One key thing to notice here, and which will be essential in the following proof, is that if we permute the homomorphisms, if we take another, say, k homomorphisms in the rows, I mean, if we use the same k homomorphisms but permute them differently along the rows, the coefficient in front of the determinant will still remain the same. This is because just the lambda is commute, and this means that we can group determinants in terms of k tuples. So for each k tuple of homomorphisms, we can consider those determinants in which that k tuple appears in the rows. Each group will contain exactly k factorial possible. Might be. Let's just first notice the following. If there are two homomorphisms are same, so if we have two rows in which the same homomorphism appears, then those rows will be proportional. This is just the fact that they are the homomorphism is multiplicative, and the constant of proportionality will be something like phi of ai minus aj. So if the two rows are proportional, then the whole determinant must vanish. So we can just disregard all of the k tuples S1, all of the k tuples of homomorphisms when two homomorphisms repeat. So we can write the above sum as the sum over all different S1 up to Sk times some constant in front of the determinants coming from the lambdas, and then times the determinant in which we substitute the first phi in the first row with phi1, phi in the second row with phi s2, and so on. Now, because as we have noticed, the constant is the same as long as we permute the homomorphism. Let us just group the determinants which have the same kind of homomorphism. Let us group them. This will make the sum into the sum of all k tuples. Now we can order them so that we don't have repeating k tuples, times some constant which can be pulled in front because all of the determinants in the parentheses have the same constant, and then times all of the possible permutation of these homomorphisms, all of the possible assignments of these homomorphisms to the rows of the array. We know that the above sum is non-zero, so we have grouped it into a sum of several smaller chunks of sums. So it follows that there exists at least one smaller sum which is itself non-zero. So this means that we can choose a k-tuple of homomorphisms. Let's just consider those k homomorphisms, such that when we sum over all permutations of the determinant and assign all possible assignments of the homomorphisms to the determinant, that sum must be non-zero. So at this point we have transformed our previous sum. We have to notice that the first sum is non-zero, therefore there exists at least one k-tuple such that the sum in the parentheses is itself non-zero. Now we have transformed our determinants from something non-multiplicative, which is phi, into determinants of the kind phi, some homomorphism of ai plus bj. However, we also have the summation sign on the left. This is a bit better than what we had. However, it still doesn't give us what we want. If we expand this determinant, we will get again the entries of the kind ai plus b tau I. However, all of these entries will be non-negative, and this just doesn't reveal any information about what we want. Well, the idea is of how to fix this, and here we will need the fact that f has characteristic 2, is to use this sum over permutations and to transfer the burden from the sum to the determinant and vice versa. So what we do is expand the determinant into a sum of permutations, then we swap the two sums, and then we compile the inner sum into again into a new determinant. This only works if we can forget about signs. So let's just recall that f was of characteristic 2. So when we expand the determinant, we can just forget about signs. So the basic idea is the determinant expands by definition into a sum of permutation of some products. Then we change the variable in the summation, then we swap the sums, and then compile the inner sum into another determinant. Let's just briefly go through what the equations mean. The first one is just simply expanding the determinant by the definition. So in the first equation we simply expand the determinant according to the definition. In the second we have a change of variable. We have a product, instead of product over all I, we take the product over all pi inverse of I, because pi is a permutation and the products commute. This is the same product itself. The third sum is swapping of the two sums, and then noticing that summing over pi inverse over all permutations pi is the same as summing over all pi, because pi inverse appears on the right, and as pi runs through all permutations, pi inverse runs through all permutations itself. Now we can notice that when we swap the sums and look at pi here, we have the expansion of another determinant. So we have a sum over all permutations of products of a kind a pi I plus b tau pi I. So we can see that this is a form of another determinant, and compile it back to get the last sum. Now, because the previous sum was non-zero and these are just identities, it follows that the last sum is non-zero. Well, a key why the proof fails when we include signs is that in the change of variable, signs don't behave well, and we end up with the last expression we end up is not the expression of a determinant. So just to recap, what we do is expand the inner determinant into according to definition, then change the variable, swap the sums, and compile the inner determinant again. Now, if we had concluded previously that we had a sum of determinants which is non-zero, and therefore we have one determinant which is non-zero, we wouldn't have gotten anything because it would just be a product of non-zero entries, and that expression doesn't tell us anything about the behavior of the ai plus b pi I. But the later determinant has exactly what we need. We can say that because we sum over all permutations of all determinants, and that sum is non-zero, it follows that at least if the sum of some numbers is non-zero, then at least one of that numbers is non-zero. So there exists a permutation tau such that the determinant in which the columns are determined by aj plus b tau j, this determinant is non-singular. But the rows are determined by I, and the columns are determined by aj plus b tau j. Therefore, if two of the entries aj plus b tau j were same, then the two rows would be completely equal, and therefore the determinant would vanish. So it follows that no two rows can be equal because the determinant is non-zero. Therefore, no two entries aj plus b tau j can be equal. So we can conclude that this is the tau we want. The numbers aj plus b tau j are k different numbers. Well, in the proof, it was essential that f was of characteristic 2. If f was not of characteristic 2, then in the second equation, when we change the variable of summation, we don't get what we want. At the end, we end up with sum over all permutations of some product, but the signs do not match with the signs we would like in a determinant expansion. So f has to be of characteristic 2. And because f is a finite field in this case, f times is cyclic. So hom g f times is isomorphic to g if and only if the exponent of g divides f times, the size of the cyclic groups. We assumed even more in the, because we could have chosen f to be arbitrary, we assumed even more than that the size of g divides the size of the multiplicative group of the field. Because the size of the multiplicative group can take any values of 2 to the power of m minus 1. We can make that divide any odd number, but we can make that divide even number because 2 and an even number are not a co-prime. If the number m is odd, then we always can choose the power. For example, we can choose 2 to the phi of m when find some the Euler's torsion function. We can always find the field we want of the desired property so that hom g f times is isomorphic. This shows why this method fails for if g has even size. Also shows why this method can be extended in another direction, because if g is, for example, not commutative, then there can be as many homomorphisms as the size of g. But we can ask some additional questions. For example, suppose that g has even size, then the Snevily's conjecture as is does not hold true, because, for example, we can take any even size subgroup, let the sets both be that same even size subgroup, then it will fail. It will even fail if we let both sets be translates of that even size subgroup. But it seems that these even sized subgroups are the only obstruction to this. So what if we ask the following question? As far as I know, this is still open, and I have no idea what the answer might be. It says that suppose we have the other case. G is still finite abelian, but G has even size now, and A and B are subsets of size k. Now suppose that we have the additional restriction which is not present in Snevily's conjecture, is that neither A nor B is a translate of some even sized subgroup of G. Is Snevily's conjecture then true? Can we pair up the elements into pairs such that each element of A corresponds to exactly one element of B, such that the K sums are all pairwise different? As far as I know, this is open, but my guess would be that this is false, and because it's just too much to hope for that these are the only counterexamples. Another question, which is probably more complicated and it probably can't be answered easily, is that what happens if G is non-commutative? When is Snevily's conjecture true? When, say, G is non-commutative and we have same size subsets, when can we pair up the elements so that the sums are different? Again, this will be probably much more difficult because non-commutative groups are much less understood than commutative groups. Probably what will happen is that there will be some groups for which this will be true, and there will be some groups for which this will fail, but probably the answer won't be as neat as we would like in a theorem. This approach cannot possibly be extended to neither of these two cases. For example, if G has even size, then we never use the fact in at least one of our lemmas, we never use the fact of what kind of structure A and B have. So there aren't enough homomorphisms in this case, and we cannot apply we cannot apply our approach here. For the second approach, again, if G is not commutative, there won't be enough homomorphisms in this case, and the most we can say is if, say, something there lies some commutative subgroup, but this is just implied from the original version of the theorem. So as far as I know, both of these questions are open, and I believe that the answer to both questions is not as neat as we would like. This would probably require a new explaining what happens in these cases would probably require a new approach. So that's it.
Any questions?
At least for the first of those questions, one could imagine just searching on a computer or something for a small counterexample.
Yeah, well, I believe that small counterexamples are searched for and that none have been found so far. But this doesn't mean that the conjecture is true. It might be, but I believe that it's false in this case.
If you already know that A plus B is large, does this help you find an appropriate permutation?
Well, not really, because they are completely different. The two are completely different questions. Well, the one in Cauchy-Davenport, the only thing we could say is really large, that if all the elements are different, then we have a different permutation. If it's slightly smaller than that, we could still conclude something similar, but we probably wouldn't get some good bound, only depending on how large the sum A plus B is.
I'm just thinking of what tools are available for identifying subgroups of abelian groups from combinatorial input like kinases.
I have no idea about it, but I believe that this will only apply if the sum A plus B is really large compared to what A and B are. I mean, close to k squared of that size, not linear. So in the general case, it won't apply.
So you showed that among the k factorial permutations there is one, so that this permutation, the restricted sum set, is going to have size at least k. Yeah. Is there any hope that there will be some small family of permutations, maybe a constant number, say 3, so that among this say 3 permutations, there is always one of them which will give you a large sum set, or is it like some expander graph,
Or indeed, are there always many permutations that give you?
or there are many permutations.
Well, in the way we prove it, this is just a purely existential proof, so we just show that the entire sum is non-zero, therefore one entry is non-zero, so we can't say anything about the other entries. And also, the method seems not to be able to be modified substantially, so in order to prove that get some lower bound on the number of permutations, we must have a completely different approach than this.
Is it clear what one might expect then? I mean, there are presumably some examples where there aren't that many permutations that work. What happens if A equals B equals just a group?
Well, if A equals B equals just a group, then, well, in that case, there should be.
1 over E or something? Is it?
These are roughly n representations. You need to kill them all.
We can assume that the first set is labelled 1 up to
Yes.
K, and then there's a permutation for which the elements I plus pi are instead. We can talk about it over tea or something. Sorry, Tim.
Again,
So,
another question. Proof is, I really enjoyed that, and but it seems to sort of rely on this, to me at any rate, unexpected simplification. It's easy to see that you can expand the function and expand everything in sight, but then at some point it all simplifies, and you rely on that very heavily. Were there any sort of precedents for it? Was there any reason to expect that this
I don't think so, and
approach would
I
work?
think that that's one reason why it can be applied to other scenarios. The proof is just well fitted for this case. It relies too much on the way the determinants simplify. Maybe if we want to do other applications, most of the proof is just some coincidence in the simplification. So
Did you just expand it speculatively to see what would happen, and then find that it,
yeah.
to your delight, it simplified?
I think this is just a hunch. The point is that actually the matching is accounted by some kind of permanent, and if it's a characteristic
Then you've
too,
got permit equals
then it's actually
determinant.
determinant, and you can expect a much nicer decision geometric properties.
Maybe I could ask a more restrictive question. Are there other examples of problems where characteristic 2 turns determinants into permanents has been used, or is this a...
As far as I don't know, that's
That's
why
very
it's
nice.
specific. That's why the method can be used for other applications, probably. So it seems that like the method is just fitted for this particular application. So it's not generally a method; it's just a proof of exactly one thing.
Other than a proof of negative. Anyway, let's thank Bodan